So I've started recording now. Each time I forget, if you guys could remind me, that would be great. So thanks, Pamela, for reminding me. So in this course, we see how you can actually use transistors as switches. Switches means a switch means something that you can turn on and off and let current pass or block the current. And the good thing about these electronic switches is that they're not mechanical, so you don't need to push anything. There is no handle. You just give it a signal and tell it to turn on, and then you can give it another signal or remove the signal and it will turn off. And you can do that much faster than a mechanical switch. So you can do that in a fraction of a second. So we're talking about maybe fractions of milliseconds sometimes, or even in microseconds. Imagine you could basically switch on and off. Imagine a mechanical switch that you could basically switch on and off in microseconds. That's basically what these switches can do. So transistors, for junction transistors, bipolar junction transistors, BJTs, we saw that we have two regions that were not used in the previous course. So the saturation and the off region were not used that often. We were only working in the active region all the time. And the same happened for field effective transistors as well. Here, when we are using the transistors as switches, we are only operating these transistors in those two regions, so the saturation region and the off region. Okay. Now, the picture that you see here is actually the drivetrain of a Tesla. Have you guys seen this before?
Yeah.
So I think it was in 2011. I was in the States, and I think there was it was Tesla had just came out. It was like the 10 or 11 where they had like these showrooms, and I was in the States, and I went to one of these showrooms, and they had this thing, this whole chassis in the room, and I asked the guy, "Where's the motor?" And he pointed to it. Do you know which one of these is the motor? It's this one. This is the motor. And not the entire thing, only from here to here. This is a gearbox, a one-step gearbox. That means it only has one gear in it, or one step in it. And then this is the converter. And this thing, this gives you the same amount of power as a BMW Roadster. Have you seen those Roadsters? I mean, when you look at it, the entire car is the engine. Let me see if I can find the actual picture. Let me see if I can share this with you guys. This is the Roadster. So that little engine, let me see if we can actually see if I can find the picture of the engine. Here it is. So that little guy that I showed you in that picture gives you the same power as this thing here. Look at the size of that and the size difference. Okay. So essentially, this course is the gateway to designing things, power electronic systems that can not only control a motor, an electric motor of an electric vehicle, but also so many other things. I mean, these days it's hard to find an electronic device that doesn't have some kind of a power electronic circuitry in it. From digital clocks to switching power supplies to bigger stuff like high voltage DC transmission lines. I mean, the influence that power electronics have had on our lives is just tremendous when you think about it, and the kind of things that they let us do now is just amazing. So, but I keep saying power electronics, but what is the actual definition of power electronics? Before we go into that, these are the reference books that we'll be using this course. So the main one that I'll be following closely is your first reference book, the one by Rashid. This is a Pearson publication, and I think I've given you the link to the publisher, so you can either do a 120-day rental, I think, of the e-version, or you can order it online. And then the second book is one by Mohan. I'll be using some examples from this book. So the first reference book is our main reference book. Okay. Now, as for the course coverage, I'm hoping that we could basically do the first 6 chapters. So chapter 1 is what we are doing today, which is introduction and basically an overall view of power electronics. In chapter 2, we'll look at power diodes. You were introduced to diodes and diode circuits. Here we'll look at diode rectifiers in more detail. So we'll introduce you to power diodes, which are designed specifically for power applications, and then we look at diode rectifiers. And then we'll look at power transistors, so transistors that are designed for power applications, and then we'll see how we can use those transistors in all sorts of converters, such as, for example, DC-DC converters. And then in inverters. So we have rectifiers, converters, and inverters, RIC. Okay, these are the 3 main categories of power electronic circuits. Now, as for your marks breakdown, this is how the marks are assigned. So it's similar to your electronic course. So we have a final exam that accounts for 30% of your overall mark, the midterm, then the Kahoots, 10%, and then labs that account for 30% of the mark. As for labs, Again, since this is one of those courses that I'm designing it as we go, I did not have any material or inherit any material from anywhere else. This is that I have to create. I'm thinking of creating 3 labs that are kind of lab projects, so they're a mini project that you can do at home. And the part that I want you guys to do is mostly simulation, so that you could do it in MATLAB. Now, since I also wanted to have that basically hands-on experience, I'm thinking of basically having my TA go to the lab, perform some of these experiments using the equipment that we have, and video it. So we are in the process of hiring someone to a co-op student who's familiar with making clips and videos, to come and make a professional video of the experiment, so that you see how the system is set up, and also have some data that you could basically use to verify your simulations and vice versa. Again, but there are still a lot of things that are not confirmed. For example, I'm not when we're gonna have, for example, the co-op students is not confirmed yet. So you have to be a bit patient with on the labs. I don't think we're gonna have a lab in the first probably month of the course. So if everything goes well, we will probably have one lab. We will have our first lab either in the 4th, and if you're lucky, maybe in the 3rd week. So 3rd or 4th week is when we're going to have the lab, and there's going to be maybe 3 labs. So one on rectifiers, one on DC-DC converters, and one on inverters. Any questions so far? No questions? Are you still there?
Just no question.
Yes.
Okay, good. Okay, so moving on. These are the things that we'll be talking about today. So I'm going to give you the definition of power electronics, power electronic switches, what is the ideal characteristics for those switches, and what kind of things would you see in a switch manual sheet or a spec sheet, for example. What are the categories of power electronic switches? How do you select power electronic switches? And some examples of power electronic circuits. So we are in the introduction part of our course. So what is power electronics? So there are so many different definitions, but one of the ones that kind of resonated with me and came from the Rashid book is that it says power electronics may be defined as the application of solid-state electronics for the control and conversion of electric power. So power electronic devices are therefore devices that allow us to convert electrical energy from one form to another in an efficient, clean, compact, and robust manner. So in other words, power electronics are things that let us control and shape the electrical power. And so with them, we can basically meet the energy utilization desired needs. Now, in in the power electronic world, we have three main sections. The power electronic basically combines power with electronics and control. The control side deals with the steady state and dynamic characteristics of closed loop systems. So I think in the third or fourth year, we'll have a linear control course, and there you basically learn how to basically design controllers for different systems. So what a controller does is it responds to changes of input. So if the input changes, how should the output change? Should the output change, or should it be maintained, etc.? So with power electronics, control is a main part. So you have to basically be able to control your system to get the desired output that you want. In light of the inputs changing, the environmental conditions changing, etc. And then we have the power side. So the power deals with the static and rotating equipment, rotating power equipment for the generation, transmission, and distribution of electric energy. So one of the main markets of power electronic application is the power industry. So things like the machines, electric machines, transmission lines, all sorts of compensators that help improve the quality of power. These things, I mean, regardless of the power electronic device that you're using to tap into, for example, the machinery world, the machine itself, you have to know how it works. What are the controlling inputs to be able to utilize or design the correct power electronic device for it. So, for example, you have to know how a DC motor works to be able to select or design a power electronic that could control its speed. Okay, so the power side deals with the equipment that the power side of things, and the equipment that you want to control, basically. Now, the electronics deals with the solid state devices. So remember that the power electronic devices are made up of solid state switches, transistors, essentially, diodes and transistors. So and those switches need certain requirements to turn on and turn off, have properties. They need circuitry that controls how they work. So, for example, if you're using a MOSFET, for example, the MOSFET needs a circuitry that gives it the gate source voltage to turn it on and off, right? So that needs a circuitry. So the electronics deals with that side. So to be able to design a power electronic device, you have to have knowledge in all these three areas to be able to basically design the device that can do the job. So as I said, power electronics is basically primarily the solution of power semiconductor devices. In all power electronic equipment, there are two main parts. One is the muscle, which is the switch module or the switches, and the other one is the brain. So all power electronic equipment have a muscle. The muscle is usually the switch. So, for example, the FET, and then the circuitry that controls the FET. So the circuitry is the brain. This is the brain, and this is the muscle. Now, power electronics are relatively new, but but they've been around for quite some time. The first utilization of something that was similar to a modern day power switch was the mercury arc rectifier. So this was something that was used in the early 19th century to change AC into DC. Okay. But the utilization of these devices, which were mostly in the form of mercury lamps, were in radios. And you probably have heard the term transistor radios, right? So transistor radios were these old radios that had a mercury lamp in them, which was basically its job was which worked similar to a diode and sometimes even a transistor. But the actual revolution, the first wave of the power electronic revolution, happened in late 40s and early 50s, when the first silicon transistor was made, and then ever since. So, for example, the PNP transistor was designed in 1956, and ever since, I mean, these devices have been utilized in various industries. I mean, these silicon controlled rectifiers were the thing that actually took us to the moon. So the first the Apollo 11 that went to the moon, but actually one of the first users of these transistors. And then you can see basically the trend in the usage and also the technology, the improvement, excuse me, in technology, and all of this is basically because of the improvements and the breakthroughs that the electronic, not just the power electronic, but also the electronic industry had. I mean, I was reading somewhere that said if you look at the breakthroughs and the trend that the electronic industry had over the past century, and if you model that to another industry, like for example the transportation industry, if the transportation industry had the same trend, now you could go from coast to coast in 8 seconds for as less as 50 cents. So that's the amount of that's how much electronic industry have improved and you know, over the past 50-60 years, and power electronics was part of that. Now you can basically I mean, even when I was growing up, if you were going from a 60 hertz country to a 50 hertz country, or from a 120 volt country to a 240 volt country, or 230 volt country, you had to take yourself an adapter. And the adapter was a big transformer. It was heavy and bulky. I still remember that. But now you can basically you can basically plug your iPhones into any wall, and you don't even have to think about what the frequency or what the voltage is. The charger that you use for your iPhone is so small and light that can fit into your pocket. And it's cheap as well, relatively. And the reason we can do that is because of power electronics. So ever since the tubes, these mercury vacuum tubes, so many other devices, the power electronics have been designed and are used in technologies. So with the improvements to both the power component and the brain, many new applications are also emerging, in which the equipment cost and dimensions have both been reduced significantly. The third wave of power electronic revolution happened in the 90s because there was a major drop in their price and improvement to their quality. So the third wave has gained momentum since the 90s, and it's affecting the way we generate, transmit, and distribute power. One of the reasons renewables can nowadays easily be integrated into our conventional power system. Remember that the power system is a 150 year industry, right? Most of the power infrastructure that you see in the city, they're quite old. Now you're integrating renewables, which is something that was created in the past 10, 20 years, maybe 30 years, into something that is 150 years old. One of the reasons you can do that is because power electronics have found their way into the power generation, transmission, and distribution as well. So with the rise of renewables, electric cars, and robots, where power electronic circuits are an essential part, this new wave of power electronics is reshaping the world around us. Okay, now that's basically the intro and the history, but what are the power electronic switches that I keep referring to? So there are many types of power electronic switches. Each one of them has its advantage and disadvantage, and was designed for some specific application. But the thing is, these devices, there are so many new devices because each one of them represents an area where the technology allowed us to create that device. So for example, the first power electronic device or switch that was created was the diode. Okay? Diode is a switch that you cannot control. And when I say you cannot control, it means that you cannot determine when a diode turns on and when it turns off. It turns on when you give it, when the voltage on this side is higher than the voltage on this side. But that's not something that you can control. That's just the input, a characteristic of the input to that switch. When the diode is on, you can't force it to turn off. And so we needed something that you could control when it turns on and turn off. And that's why a thyristor was created. So a thyristor is basically a diode that you can control when it turns on. So with a thyristor, if you give it a sinusoidal input, you can control whether it's on here, here, or here. So you can control when it turns on, but you can't control when it turns off. That's why TRIAC was created. And then from then onwards, we have MOSFETs, IGBTs, BJTs, and GTOs. Okay, so with a TRIAC or with a thyristor, you still need this positive-negative voltage difference for it to turn on and off. With MOSFETs, you can turn them on at any time. It's like a switch. The same with IGBTs and BJTs. So in the power electronic world, we have this thing called the ideal or the super device. These switches, all of these switches were made to get closer to this super device that has a set of characteristics and properties that would make it really handy and really easy to work with. Okay. And the characteristics of any real device can be compared and evaluated with reference to the ideal characteristics of a super or ideal device. So what is this super device, and what are these ideal characteristics? Well, imagine a diode if you imagine a diode, when the diode turns on, it can pass current through, right? But if you grab an electronic diode, you cannot pass, for example, 1000 amps through it, right? An ideal device in the on state, when the switch is on, has the ability to carry a high forward current tending to infinity. So we want the switch to be able to handle high levels of current. A low on state forward voltage drop. So remember that a diode, you have to give it at least 0.7 volts, right, for it to turn on. If you have a voltage difference that is, for example, 0.5, it won't turn on. And when it turns on, you still see that 0.7 voltage drop across it. So we want this on state forward voltage drop to be as low as possible. So not 0.7, but 0. A low on state resistance. So when we were talking about the model of a diode, we had a resistor and a voltage source in series. This resistor is a source of voltage loss and power loss. So we want this R on to be as close to 0 as possible. And if this forward or on state resistance is 0, then you won't have power loss either, right? So we want the on state power loss to be 0. In the off state, we want the switch to have the ability to withstand a high forward or reverse voltage tending to infinity. Remember that, for example, for diodes, they had a limit on how much reverse voltage you could apply to them. They had a breaking point. Remember that? So we want this to be as close to infinity as possible. That means that we could basically apply any reverse voltage to the switch and it won't break. A low off-state leakage current. Remember that semiconductors, they are not full insulators when they're off. You still have a leakage current even when the switch is off, but since the leakage current is in microamps, you usually ignore it. We assume it to be 0, but we want that leakage current to be absolutely 0 because in electronics, microamps is still sometimes can have an effect. And a high off state resistance. So we want in the off state, the diode still has a resistance. I mean, the resistance is usually in the tens of kilo ohms, but there is still a resistance, which means that a current can go through, and even the switch is off, even when the switch is open, you still have power consumption. We want this resistance to be infinity so that the diode in the off state works exactly like an open circuit and does not consume any power. It's like you want your TV to consume no power when you shut it down, right? But we know that when you put your TV in standby, it is still consuming some power. Now, in the AC mode, remember for transistors, when you apply, for example, to a MOSFET, when you apply a gate signal, it takes the MOSFET a while to turn on and a while to turn off. It doesn't happen instantly. So that's why for the voltage across the switch, you don't see a drop here. It takes a while for it to drop. It ramps down. And then when you turn it off, the voltage across it does not go back to what it was before immediately. It takes a while, ramps up, right? So it's like the current going through it does not jump to its rated value. The current ramps up and then ramps down. So we want these ramps to be straight lines. So we want the switch to turn on when we tell it to and turn off when we tell it to. So we want these to look like this. So not trapezoidal, but square. So we want all these delay times, the delay time, rise time, storage time, and fall time. We want all of these to be zero, as close to zero as possible. Does anybody know what that gives us? Like if you have these delay times tending to zero, what could we do with the switch? What is wrong with having delay times or rise times or storage times? I mean, these are in milliseconds and nanoseconds, but why do these bug us so much that we want them to be as close to zero as possible? What could improve if these tend to zero?
Is it the energy efficiency?
Energy efficiency is one of them. What else? Anyone? Yes.
Does it make it just faster to have a power electronic without as much delay?
Can you give me an example of that in real life? What would change if you didn't have these delays?
Then there wouldn't be as much of a time period where it's in a transitory phase. Like it would lessen that and then make it like for if you're using a power electronic that has the need to turn on and off a lot. Because like if it's in AC, then it's alternating current. So then you don't want to have a long delay time because you want to have a steady operation of the electronic. I don't know a specific example, but I believe most would operate like that.
I'll give you one example. When you install software on your laptop, it wouldn't take 5 minutes. It would take 0 seconds. So one of the reasons we have delays in electronics and we have speed limits in, for example, computers are these delays. I mean, you cannot basically turn on and off switches. If you cannot turn on and off switches, these transistors, then you cannot basically put gates that are made of these transistors after one another and expect them to work with whatever frequency you give their input. Because, for example, this has not changed state, and this is now changing state because of these delays. These delays cause the speed limits that we have, for example, with our electronic circuits, with the electronic equipment. And as Pamela said, they also cause switching losses. So when this switch is turning on, the voltage has not completely dropped to zero and the current is moving up. So when you multiply these two by each other, you get this power curve that looks like this. And this is how much power you're losing every time the switch is turning on and off. And we want this to be as minimum as possible. If these were happening instantly, the power would look like spikes. You would get spike powers, not something like this. So you would lose way less power than what you're losing now, except these ramps. And the other thing that we want for the super device is for the power that you need. That means that the voltage and the current that you need to turn the device on and off to be as close to zero as possible. So we would basically want the switching to be effortless, right? So you would give it a really small voltage and almost no current. The switch would turn on. Same thing, switch would turn off. The other thing is that we want both the turn on and turn off to be controllable. So like, for example, thyristors, you can turn them off, but you can't turn them on. A diode, you can't turn on and you can't turn off. You have no control over when the diode turns on or off. It's just governed by the input that you give it. You yourself have no control over it. But for example, with MOSFETs and FETs in general, you can turn them on and off by the voltage that you apply here, right? For turning on and off, it only requires a pulse signal that is a small pulse with a very small width. So we want the switch to turn on with a pulse. If we use a BJT transistor as a switch, you can basically control it, so you can turn it on and off with a signal, but the signal has to stay, right? I mean, the voltage that you're applying here must be sustained for the transistors to stay on. The moment you take this voltage away, the transistor switches off. We want something that you would just give it a pulse, it would turn on, and you would give it another pulse, for example, a negative pulse, and it would turn off. You wouldn't need to keep the signal there for it to stay on, and because that would basically require more energy and more complicated circuitry. So we want the turning on and off to be pulse-like, not sustaining signals. And we want the device to have a high dV by dt. That means that we want the device to be able to handle rapid changes of voltage across it. A lot of transistors, you cannot change the voltage across them too fast. it'll damage it. So that means that the frequency that you can apply to them would be limited. The same thing for di by dt, that means the rate of change of current. You cannot expect a switch to shut down, for example, tens of thousands of amps in 1 second or in instantly. It cannot. It can only handle so much current. It requires very low thermal impedance from the internal junction to the ambient. So you guys have studied heat transfer, I guess, right? Did you have heat transfer last semester, or do you have it this semester?
We're having it this semester.
You're having it this semester. So one of the things that you learn is that for two different materials that are connected, each one of them have a resistance, a thermal impedance, if you like. And the thermal impedance shows how easy the material can pass the heat to the next one. So for example, if you have two metals usually have really low thermal impedance. That's why when you touch a hot metal, you feel the burn. But plastic, you feel the heat, I mean. But plastic, if this one was metal and this one was plastic has a high thermal impedance. So when you touch it, this is someone's hand. Sorry, my painting is awful. If you touch it, then you won't get burned because the impedance is high, so it doesn't transfer the heat as good as the metal. So sometimes that's a good thing, and sometimes that's a really bad thing. Because, for example, let's say you have a chip, an IC. You have so many transistors in the tip of a match, for example, and they're heating up. If you can't get the heat out, then you're going to end up with hot spots that's going to burn the IC. That's why, for example, for computers, when you look at the CPU, they have a giant heat sink on top of them. That giant heat sink is cooling off something that is the tip of a of a match. So we want these switches to have good heat transfer capabilities so that they wouldn't get hot, and we could basically use them in places that are small. Then we want them to be able to handle fault current. So we know that the switch is rated for 100 amps, but it should be able to handle 1000 amps for a few seconds and not get burned. We want the ideal switch to have a negative temperature coefficient. That means that when the temperature rises, its resistance does not go up, but rather goes down, so that it can handle more current. Okay. And finally, we want it to have low prices. So we want all of this for as cheap as possible. So these are the characteristics of an ideal switch. Now, each one of those switches that I showed you have some of these properties, but not all of them. Any questions so far? No? Okay, let's move on. So when you buy a switch, there are certain specs that are really important that everybody, especially those who design power electronic systems, they always check these specs, and these specs are more or less the same as what we were talking about in the previous two slides. So the things that are important when for power electronic switches and are usually mentioned by manufacturers in the spec sheets. The spec sheets are the voltage ratings, so the forward and reverse repetitive peak voltages and the on-stick forward bias voltage drop. Current ratings. So what is the average amount of current that it can handle? What is the RMS current? What is the repetitive peak, non-repetitive peak, and the off-state leakage current? So these are the things that you'll see in their data sheet. So for example, if you buy a transistor, a BJT transistor, and look at its data sheet, you will see all of these voltage and current ratings. The switching speed or frequency. So how fast can you turn the switch on and off? From a fully non-conducting to a fully conducting, the turn on and also the turn off. These two are not usually the same. So it usually takes more time to turn off the device than it takes it to turn on. We can see that here as well, and just go back. So here is when you want to turn off the device. It takes this much long, and here's when you want to turn it on. So there is this storage time that also that needs to pass, and that makes the turning off slower than turn on. So you can see that the turn off is greater than the turn on. The DI by DT rating. So the device needs a minimum amount of time before its whole conducting surface comes into play in carrying the full current. So for example, if you have a semiconductor like this is its surface area. When you apply the current, not all of the surface will be utilized at once. The current will go through, for example, the middle, or if it's a high frequency current, it goes around. So it uses this much space. If the current is too much, or the DT rating, the rate of change of current rating is not appropriate, then you end up with hot spots. So for example, the core will heat up and will damage the device. Or the surrounding, the edges will heat up and will delaminate the device, the core from the casing, for example. So in many real-life applications, we need to limit this. So in the spec sheet, you are given the DI by DT rating, and for your application, you have to put a snubber circuit. A snubber circuit is something that would delay the rise of current. I mean, in circuits, we looked at RC circuits, right? With RC circuits, when you apply a voltage here, it takes a while for the capacitor to charge up. So if I draw the output voltage versus the input voltage, this is the input voltage, the output voltage would look like this. So that means that if you are giving the circuit something like this as the input, it'll take sorry, I'm talking about dV by dt. This is di by dt. So instead of a snubber circuit, we put an inductor, and the inductor does the same job as an RC network with current. So what we do is that we put a series inductor in series with the device, and what the inductor does is that it doesn't let current change instantly. So instead of, if this is the current, I out, instead of, and if the current was changing like this, the inductor makes the current into either a ramp or makes it into a curve. So it doesn't allow these sharp edges. It smooths them, right? And we call that a series snubber circuit. And dV by dt, or the rate of change of voltage, again, is important, and it's one of the things that you usually see in power electronic switch spec sheets. The reason it's important is because there is, for all power electronic switches, there is a junction capacitor. So for example, there is a capacitor here for a BJT transistor. Now for a capacitor, what is the current rating? Like, how do you calculate the current of a capacitor? Any? How do you calculate the current of a capacitor? Okay, let's see. Manning, if I have a capacitor, how do I calculate the current going through it?
Sorry, I kind of forgot it. I learned it. Do you take the voltage source and divide it by current?
So the current through a capacitor is its capacitance times the rate of change of voltage.
Oh, I see.
So the current of a capacitor depends on the rate of change of voltage. If this rate is too high, then what happens is that you end up with, again, a really high current trying to go through, and you end up with again hot spots that can damage the device. So we also want the rate of change of voltage to the device to be low. So that's why instead of giving the voltage directly to the device, if the dV/dt rating is not matched, we usually use a snubber circuit, which is an RC circuit. So you see something like this instead. And what this does is that if the voltage is changing like this, it smooths out the voltage, so you get something like this. Now, the RC causes the change to become smooth like this, and that will protect the transistor in the circuit, or the power electronic switches. Okay. Now, in this course, we'll be talking about all of these things. This is just a snapshot of the things that we'll be learning. So this is just an overview, right, of the whole thing. Switching losses, we talked about them. So you'll get a table that says what the switching loss is going to be at different frequencies. When you look in the spec sheet, you will also see gate drive requirement. So it tells you to turn on and turn off this device, what you need to give it. So what is this range of input currents and voltages that you need to give the switch. And it also shows you the safe operating area. So it should be the area where you will, for example, for transistors, we saw that the safe operating area was something like this, right? And this area was not too close to the power limit and not over the current limit or the voltage limits. and also I2T, I squared T, which is something that you need for fusing. So it shows that if the device experiences a short circuit, how long it has before it burns. And that basically tells you that if you want to protect your $10,000 switch, for example, what kind of fuse you need to use in series with it. So if this is the switch and it costs $10,000 and you want to protect it, you need to know the I squared T to be able to select the right fuse for it. And also the temperature ranges. So what is the maximum allowable junction case and storage temperatures? So for example, if the device temperature goes above 150 or 200, the device will burn, and that tells you what kind of a heat sink you need to use. And also if you're storing it, if you're not using it, for example, what is the range of temperatures that you can store the device without damaging it? Okay, and also the thermal resistance, which again, as I explained, it can be used for heatsink calculations. Okay, who's still awake?
Yes.
Okay, I got 3 people still awake. 4, 5. What about Daniela? Danielle, are you awake as well?
Yeah, I'm up.
Okay, good. So you're all awake. Okay. Now, as for what are the classes of switches? So you're familiar with diodes. You're familiar with transistors. Thyristors is something that we'll learn in this course. But as I explained, thyristors are essentially just diodes that you can control when they turn on, and in some of them, like GTOs, gate turn-offs, you can also control when they turn off. Now, in the past 40 or 50 years, most of the power electronic switches that were made of silicon. So we call them silicon-based switches. In the past 10 to 15 years, silicon carbide is also coming into play because it has better electrical and thermal ratings. So a lot of the high-tech systems that use that need to have basically good thermal and electrical rating use silicon carbide switches. So you see diodes and transistors that are SiC, that's silicon carbide. But you don't see thyristors. Thyristors are basically the grandpa of switches. They are the first set of power electronics that were power electronic switches that were created, and they are gradually given their space to other modern power electronic switches like transistors. But in high power, none of these can still match thyristors, so they are still lingering around because they can handle high powers. So as for the technology, silicon carbide technology, you can find diodes and transistors, MOSFETs only, that are made of silicon carbide. If you have a application that needs really good thermal and electrical capabilities. So this is something that, for example, NASA uses. for the Explorer, and what was the other one that they sent? The other probe that they sent to Mars? Discovery and Explorer, I think they were, right? So if you go to work for NASA, when you're selecting switches, you need to be using something like this, like silicon carbide switches. Before we move on, I want to spend a bit of time just on getting you familiar with some of these devices. So looking at diodes, we talked about Shockley. Does anybody remember what Shockley Schottky diodes were? No? So Schottky diodes were those fast-acting diodes that you could basically that would follow the equation of Schottky. So you may need to go back to the note from circuits for that. For transistors, we looked at BJTs, and BJTs are also kind of becoming less common in industry. So it says low importance on market. So those, the ones that are shaded, are not, don't have a big market. BJTs are losing their market. I don't think, apart from universities, that many other places are using them. The reason for that is because you need a current source to turn on and off the switch. And currents are not easy to make, but voltage sources are easy to make, right? So transistors work with a current source, but FETs, they work with a voltage source, so they're much easier to control. That's why you don't see BJT transistors in the industry that often. Instead, you see MOSFETs and IGBTs. IGBTs are transistors that have the good properties of BJT, but they turn on and off like a MOSFET. So it's like a BJT that you can turn on and off with a voltage source. The good properties of BJTs are the high voltage and current ratings that they have. So the current ratings of BJTs is usually much higher than MOSFETs. So IGBTs were designed specifically so that they would have the good current and voltage ratings like BJTs, but they would turn on and off like FETs, like MOSFETs, for example, with a voltage source. Now, does anybody know where IGBTs are usually used? Have you ever heard of something called IGBT? Have you ever come across this name or this device?
I've never heard of it.
Anyone else? So if you go in any industry that deals with drives are things that control the speed of a motor. Any industry, so that goes from pulp and paper to cement plants, any industry that deals with some kind of a motor that needs speed control and drives, you'll hear IGBT a lot, because that's the thing. Those are the switches that are used in almost all of the drives these days. So in industry, most drives are called VFDs, variable frequency drives. The switches inside VFDs are all IGBTs, and you hear that this name a lot. The older type of drives use thyristors, So if you ever come across old engineers or more senior engineers, they're more familiar with thyristor drives. But most of the drives in the industry nowadays are IGBT drives. That's a piece of knowledge, general knowledge for you guys. Okay, now this one sounds really similar to this one, but it's of a different category, and remember this. So IGBT is a transistor, but IGCT, insulated gate converted thyristor, is a thyristor. Can someone explain what is the difference between? So a thyristor is kind of a diode that you can control. You can control when it turns on and off. Can someone explain what is the difference between a diode and a transistor when you use them as a switch? What makes diodes different from transistors?
There still has to be a voltage difference between a diode, whereas a transistor you can control it regardless of the voltages.
Very good. I was about to give 1%, bonus 1%, but then you had your hand up. So so you'll be my first candidate for the next bonus question. How's that? So with as Mackenzie said, the difference between diodes and transistors is that transistors you do not. I mean, you can control when they turn on and off, regardless of what the voltage is, right? With diodes, you have to have a higher voltage on this side than this side for the diode to turn on. And thyristors are like that as well. So for a thyristor, you can control when it turns on and off. So if this is the input, if you give this as the input to the thyristor, you can control when the thyristor comes on, but you can't control when it turns off. So it turns off here. IGCT lets you control when it turns off as well. So you can turn it on here and turn it off here. But you still need this higher voltage on this side, higher voltage in this side than this side for the switch to turn on. That means that, for example, you cannot turn on the switch here. It has to be on this side. You can turn on this cycle and you can turn it off on this cycle. That's the difference between transistors and diodes. So IGCT, that sounds really similar to IGBT. This is a thyristor. This one is a transistor. And then also gate turn-offs. These two are more or less the same thing. This one just has better properties than GTOs. So, yes.
Wait, so did you say that in a thyristor, then you can also control when it's off or only when it's on? Like when you turn it on?
So classical thyristors, so these classical thyristors, you can only control when they turn on. Okay, but GTOs and IGCTs, they kind of enhanced thyristors. That means that you can control when they turn on and when they turn off. So if I had a thyristor, just a thyristor, I can only control when it turns on. So I can turn it on here in the positive cycle, and it turns off here, right? When the voltage is reversed. But a GTO or an IGCT, I can control when it turns on, and I can control when it turns off. So I can turn it on anywhere on this cycle, and I can turn it off anywhere in this cycle. Does that answer your question?
Yes, thank you.
Yeah. Okay. Now, moving on. Now, in terms of the range of power capability of these switches, we have a limit on the amount of current that it can handle and a limit on the amount of voltage that it can handle. Notice that we don't have any technology that goes above 6K for current. So the maximum current that a switch, one single switch can handle is 6,000 amps. And only one company has the technology for that, Mitsubishi. So Mitsubishi has GTOs that can handle 6,000 amps. And 6,000 amps is a lot. If you see the size of those switches, they're as big as maybe twice as big as some of them are as big as your laptop, for example. One single thyristor. Imagine a diode that size. At the maximum voltage that a switch can handle with our current technology is 12,000 volts. So no more than 12,000 volts and no more than 6,000 amps. And again, the same company holds the patent to that. So Mitsubishi is the only company that makes switches that can handle high currents and voltages. And the only type of switch that we have that can handle high currents is a GTO, which is a kind of a thyristor. The only type of switch that we have that can handle high voltage is SCR. SCR is a conventional thyristor, so you can only control when it turns on. You can't control when it turns off. Now, IGBTs, which are these modern switches, they go up to 2,400 amps and 7.5 kilovolts. So this is basically the IGBT market. One thing that, I mean, it was even new for me when I was looking at this graph was that the patent and the technology of all of these switches is in the hands of less than half a dozen companies. So 4 or 5 companies make all the switches that you see in any device that uses power electronics. So Mitsubishi, Westcode, ABB, UPEC, and Semicron. This one, I think, I haven't heard of it. It might have been merged with another one. I'm sorry, and Fuji as well. So Japanese and European companies like Semicron and UPEC. These are German companies. And Mitsubishi and Fuji, they're Japanese. ABB is a Swedish company, so it's jointly owned by Sweden and Switzerland. So IGBT limits is what you see here. The other interesting thing is that power MOSFET, which is the thing that is used for high switching in any type of, for example, sound system, video system, stuff like that. You need high switching, which means that you need to have a MOSFET, because MOSFET has the highest switching capability. They can only go up to 1,000 amps. You can't switch more than 1,000 amps in with MOSFETs. Any questions on this? So if I ask you what is the switch that can handle the greatest amount of current, which switch would you check? Would you pick? You go to work for a company and they need to handle 6,000 amps. What kind of a switch does the job? Yeah, Simran.
GTO.
GTO.
Yeah.
And what is a GTO? What category of a switch is it?
Is it thyristor?
It's a thyristor. Like,
Yeah.
how does it turn on and off? Can you turn it, for example, can you turn it off? Or can you only turn it on?
I think we can turn it on and off both.
You can turn it. So these are the kind of things that you need to know, like just general knowledge that you need to have when you go to work for a company that needs to handle and manage power, right? Or companies that make devices to manage power. So if you are dealing with 6,000 amps, the only thing that is available in the market that can handle that sort of event is a GTO. And the limitations of a GTO is that it can turn on and turn off power, but you can't turn it on and off at any time. You have to turn it on in the positive cycle, and you have to turn it off in the negative cycle of the input voltage. If you want a device that can handle really high voltages, the only thing that we have available is a thyristor. That means that you can only turn it on, but you can't turn it off. So you can turn it on in the positive cycle, but you have to wait for the cycle to finish for the device to turn off. Right? Now, does anybody know what is the typical voltage of a generator, a power generator, like a hydro generator? What kind of a voltage comes out of a generator? Does anybody know? So a typical hydro generator, the output voltage of it is in 20 to 30 kilovolts. So 20 to 30. If you were to use a one of these switches for a hydro generator, you couldn't. There's nothing that we have that can handle that voltage, because the maximum amount of voltage that it can handle is 12,000 volts. That's half of what comes out of a hydro generator. So can someone tell me, and this would be for a bonus point, a 1% bonus point, and Mackenzie gets the first right of refusal, if you like, or you get basically the chance. If you couldn't, then it goes to someone else. Can someone tell me, how could we use switches with their current limits? So we have a limit of 6K for current and 12K for voltage. So with these limits, how can we use power electronic switches for higher voltages and higher currents? Mackenzie?
Would you use them? Would you use them in series?
You would use series for current, and how would you use them for voltage?
In parallel.
Is it like that, or?
What am I thinking? I'm
Say
not
that
sure.
again?
I'm not totally sure how you would deal with
I give you 0.5%, because half of that answer was right. Anyone else?
Yeah.
So put volts. Anyone else wants to answer?
So the question is, how do you get the highest voltage?
Yeah, so we have 6,000 amp limit and 12,000 volt limit on the voltage. How do you use these switches on higher voltages or higher currents? If you wanted more current, for example, how would you connect switches to handle more currents? So if you want more current, you need to create more paths so that they could share the current, right? So you would put the switches in parallel. So if you put them in parallel, you can handle higher currents. If you in series, then each one of them gets a portion of the voltage, right? So if this is, for example, 100 volts, this sees 50 and this one sees 50. If this is 100 amps, 1, 2, 3, 4, 5, each one of them will handle 20 amps. So the way power electronic switches are used everywhere in all sorts of applications that have all sorts of current and voltage ratings, but each switch is only limited to these values, like, right? So for example, GTOs, they can handle 6,000 amps and 6,000 volts. If you want something that needs to handle 36,000 amp, you need to have 6 GTOs in parallel. If the voltage that each GTO sees is more than 6,000, then you need to put this package in series with another package like that. And the challenge of doing this is that if one of these GTOs comes on before the other ones, all the current wants to go through that and will kill it instantly. That GTO will burn instantly. So synchronizing these switches is a headache, and is only a few companies have the ability to do that. So I'm taking you to the very edge of the science right now. I mean, this is where the research is happening these days. If you're handling high amounts of current and high amounts of voltage, for example, so if you're putting switches in series and in parallel, how do you make sure that they turn on and off on exactly the same time? Because if one of them turns on before the other one, all the current wants to go through that. The GTO is only good for 6,000 amps, but 36,000 amps is going through it now because it has turned on before the other ones. So there are all sorts of circuits and control systems synchronizing the switches. Yes, Pamela.
Excuse the noise. There's just like construction. But and what does that depend on? Is it like the material? Like why would one receive more current than the others?
It's like two transistors. You can't find any two transistors that have the exact same property. Right?
Okay.
It's just a property of the material. It's just how these things are made. I mean, you get a bunch of more atoms in silicon. You get like maybe 100 more atoms of gallium in silicon, and then you have the transistor that you made has a property than the other one, than another one that the company made. So each transistor like even from the same manufacturer with the same part numbers, they don't have the exact same parameters. Each one of them has a slight different parameter. So one of them might have a beta that is 100, the other one might be 100.001, right? And these small changes affect how these turn on and off. Karen.
So if we want to make sure that the electronics are safe, could we ramp up the voltage so that it's not reaching that limit of, say, 6,000 volts right away? So then that way, like, it's not just blowing up, but like ramping it up and ramping it down when it's switching?
So we don't always have the option of ramping, because if you ramp it, it means you're delaying it, right? So we can't always delay things. And when you're dealing with 6,000 amps, it's already slow anyway, so you can't delay it any further. If you delay it, so if you ramp it, which means that you are delaying its operation, then you'll end up with more harmonics, and now you have to spend a fortune on filtering the harmonics. We'll get to that in later chapters, but that's the other challenge. So you can't ramp up. Sometimes you need these things to switch on the fly. So they have their internal delays, but you do not want to go over those. You do not want to basically extend those delays further, because then you end up with other issues other problems that you need to solve. Mackenzie, did you have a question as well? Did I miss your question?
No, I hit the button by accident, but I actually do have a question now. What's a situation where you would need a 6,000 amp transistor?
In what situation? Like what application?
Yeah, like what's an application where you need that level of current?
So a wind turbine. There are turbines that are 6 megawatts. 6 megawatts at 7.2 kilovolts. Calculate the current. Let's just, for the sake of argument, just say 6 kilovolts. You would have 1,000 amps, right? Now, let's say you have a wind park that has hundreds of these. So 100 times 1,000 amps, 100 kiloamps. So these wind turbines, they need to go through a centralized inverter and then connect to the grid. That centralized inverter, that has switches in it. So that means that the switch should be able to handle 100K. So there was plenty of examples. So in the Powerball, when you go into generation and transmission, everything is in megawatts and gigawatts, and so you do need to be able to handle those kind of currents. Does that answer your question?
Yes, thank you very much.
Yeah. So generation, so power generation and power transmission. Even in a smaller scale, I mean, if you go to heavy industry, there are kilns and burners where you need, like there are induction heaters that do need up to 12 kiloamps, because they work on with eddy currents, so they need high currents. Some of them need high amount of voltage, some of them need high amounts of current, but there are burners and heaters in the industry that require those range of currents. And so you do need to have switches that can handle those sorts of current ratings and voltage ratings. So in the power world, K, like kilovolts, kiloamps, these are peanuts, right? Peanut scale. Everything is in megawatts, so mega amp, megavolt. Sorry, not sorry, megawatt. I meant megawatt, megavolt ampere, gigavolt ampere. That means that your voltages will be, I mean, in transmission, you would see voltages that are in the range of 500 kilovolt or 132 kilovolt. Currents will be high as well, so you would expect the current to be 10 to 20 K. So in the transmission and generation industries and sectors, the power is usually in mega and giga range, and 6,000 is not that much. 6,000 amps or 12,000 volts is nothing. A hydro generator, just the terminal voltage of it is between 20 to 30,000 volts. And then you step it up with a transformer to 132 or 200 something. So these ranges are nothing. And that's why if you're using these devices in transmission and generation, then you need to put them in parallel, and that has its own challenges. And this is why it has taken power electronics so long to get into transmission and generation. It has been in distribution for longer. So you see, for example, PV panels on roofs. That's at distribution level, right? You see all sorts of facts and defects, which is basically power electronic devices in the distribution sector, because there the voltages and the currents are quite low. So for example, a PV panel, a solar panel that you put on the roof needs to have an inverter. The power that comes out of the solar panel, sorry, the voltage that comes out of it is DC. And your wiring, your house wiring is AC, so you need to change it to AC before you could plug it into the wall, for example, right? But the power rating there is only like a few kilowatts. It might be 1 kilowatts. In many cases, even less. So it doesn't need. So the switches in this device don't need to handle high currents and voltages. So when you look at the power electronic industry, it has started from electronics, so things like digital clocks, switching power supplies and stuff like that, LEDs and stuff like that, and it's moving its way towards other industries. So it's moving its way towards transmission and generation. So things like this, these are where most power electronics were applied. So things like power supplies, audio systems, etc., with MOSFET. So this is basically operation frequency versus power capacity. Now it's moving its way to cars, robotics. It was in drives for some time, but now it's going this way. So now you are seeing electric trains, transmission lines, so HVDC, and eventually it will move towards generation as well. Now, one of the things that I want you to remember is that the switching, so these are switches, right? The power electronic devices, like transistors, etc. These are all switches. The frequency at which you switch, you turn these on and off, determines your harmonics. So if you are trying to make, for example, a AC waveform that is 60 hertz, if that 60 hertz ends up having other harmonics in it, other frequencies, or other sinusoidals with higher voltages on it, you need to filter it out. But the thing is that we learn later on that the faster you operate the switch, the more you can push these harmonics into higher range frequencies, and it's much easier to filter out if a noise that is 10 kilohertz than it's to filter a noise that is 120 hertz, for example. So the higher the frequency, the cheaper and the easier it is to filter it out. That's why, for example, in this chart, you see power supply for audio having a frequency, a switching frequency need that is in 100K to 1 megahertz range, because for audio, for good quality audio, we want those noise or those harmonics to be as far away from the main signal as possible, so that they could easily be filtered. In motor drives, it's not that important, so you can have lower frequencies, but in things that we hear and see, we want to have less harmonics. So this is also an interesting graph to look at. So you can see that, for example, drives, they are usually in this range. So the higher ones, the ones that the bigger motors, so for example mills that crash or crushers, like rock crushers, that require high power handling capability, they use GTOs, but their frequency drops. So the frequency of GTOs is only 100 to 1000 hertz. But for other drives, smaller drives, they can use IGBTs, and so their switching could go as high as 10,000 K. For the Tesla car that I showed you, the drive is made of MOSFET, and that means that its switching could be between 10 to 100K. I think cars, they also use IGBTs from what I know. So this is basically the switching frequency versus power. So just to give you an image of when you think of these, the switching frequency and the power handling capability. So when you are switching 6,000 amps on and off, it's like opening and shutting a dam gate, a hydro dam gate, in 1 second. So the current that is coming out of the gate, just imagine a dam, a hydro dam, and the amount of current that comes out of it. You need to be able to close and open that gate. If you're operating at 1K, 1,000 times a second. Imagine the technology that requires. That's versus, for example, a hose. So when you go into electronics, it's like a water hose, and so creating a switch that could, close and open the tap 1,000 times is not that hard. If the amount of water or the amount of current that you're handling be a few milliamps, for example, right? That's why you can have power supplies for audio systems switching at 1 million instances a second, but you can't have a hydro dam opening and closing its gates 1 million times a second. You can do it maybe 100 times a second. Okay, I think we are reaching the end, so I'll leave the switch selection criteria for our next lecture. Any questions before we go? Yes.
So just to clarify again, that the power capacity you can think about as kind of like the amount of, like if you're thinking about it as the hydro dam versus a tap, it's the amount of water, this need to stop it would be a lot more for a hydro dam. So then that would be in the lower frequency range, and the higher
Yes,
frequency range, it was more like
exactly.
tap. Right. Okay. Just making
Yeah,
sure.
so just remember that power in electrical world is voltage times current, right? So if you need something that can handle high power, I mean, the voltage is one thing, but the current is the most limiting factor in all cases. So if you need something that can handle high power, which usually translates to high current as well, that's like open and having a switch that can handle, you know, the same amount of water as the gate of a hydro dam. So you shouldn't expect the switching frequency to be high. If you're lucky, you can get something that is between 10 hertz and 100 hertz, which means that you need to have more expensive filters because you'll end up with more harmonics. We'll talk about harmonics later on, but just for the time being, just remember that higher switching frequency or operating frequency means cheaper filters or less filtering, right? The same with cars. I mean, a DC motor, it doesn't care if the voltage that you're giving it looks like this or looks like this with a bit of a hash on it, right? It can still work. But if you give that voltage to a audio system, for sure you're gonna hear more noise in your music. That's why it needs to be filtered, and that's why it's better to use something that can go up to like 1,000,000 hertz for the switching. So yeah, so this basically shows how much power these different types of switches can handle in what frequency ranges. So the higher the power, the lower the frequency that the operating frequency that it can work at. For example, a washing machine, when it's turning on and turning off, it requires a relatively high amount of current, but it doesn't need to go super fast. I mean, your washing machine doesn't need to spin 16,000 RPM, right? It only needs to spin maybe, I don't know, 100 times a second or 200 times a second. Sorry, not second, like 300 rounds a minute or 500 rounds a minute. So the switching frequency doesn't need to be that high. That's why you see it here. But a motor, you may need to spin it at 3,000 RPM. It's like I forgot what they are called, but these are things that use in medicine. They use centrifugal force. They spin a liquid so that the isotopes or the different parts, different components of it, end up in different layers. Some of them need to spin at 35,000 kilo RPM. And that translates to the amount of switching that the motor needs to do. Right? For example, you have a jar mixed up of different types of material. If you spin it, and sometimes we are talking about material at an atomic scale. Sometimes, so you need to spin it fast enough that even something with that small of a mass would basically be collected in different layers. And the faster you could spin it, the more or the smaller, the more accurately you could separate these different components or different constituents of the liquid, or the smaller molecules you could separate. And sometimes you need motors that could go 35,000 RPM or 16,000 RPM. So you need switches that could basically switch that fast or even faster to operate those motors. Right? Any other questions? Yes, Imran.
It's a very general question. So why do we even need to turn it on and off, on and off? Why can't we just keep it on the whole time?
So this is kind of, we're going into the next lecture, but why do we need to turn it on and off? Do you guys have time? I mean, this might take for you 4 minutes. If you want, we can leave it for next lecture, but if you want, I can answer it now, if everybody agrees. It's actually quite an interesting topic. So if you have time, just stay behind for 5 minutes, and I'll give you a good analogy for that. Let's say you have a some kind of a device, right? This device needs 25 volts to work. You have a power supply. The power supply is 100 volts. How do you step down the voltage so that you could supply your CD player or whatever, your device? This is your load, for example, right? It could be anything. How do you step down 100 volts to 25 so that you could supply your load? Anybody?
You can use a transformer.
So this is DC. It's already rectified. So I've got 100 volt DC. The voltage looks like this, right? I want to go from 100 to 25. How do you divide voltages? What was the voltage divider rule? Remember that? So if I put two resistors here, R1 and R2, I can choose these two resistors so that I could basically divide the voltage. So I want the voltage to be divided by 4. So let's say I pick 3 and 1. So I've got 100. The voltage across this R2 is 100 times 1 over the sum of the two, so 25. Right? Now I can connect my power supply to the load. Right? Now here's the thing. Let's say your load had an internal resistance of 10 ohms. So that means that and you had to give it 25 volts. So what was the power consumption of the load? 25 volts, resistance 10 ohms. What would be the power consumption? (25 squared over 10 would be 62.5 watts, right? So the load only needs 62.5 watts. Now I'm connecting my voltage divider. I mean, I've passed circuit, so I should be able to do this, right? So I connect my battery to that electronic circuit that I had, and I've divided the voltage using 2 resistors. How much is the power consumption now? So how much power is the source providing now? Can you guys calculate that? I mean, it doesn't get simpler than this. It's 2 resistors, sorry, 3 resistors actually. So these are my 3 and 1 ohm resistors. This is the load. That is 10 ohms. Connecting it to a battery that is 100 volts. How much is the power consumption? I've got 3 resistors, they're all consuming. So my R total would be 3 plus 1 in parallel with 10, which is more or less the same as 3 plus 1. 4 ohms. So the total power now is 100 squared over 4. What does that give you? 500 watts. Your device only needed 62. You basically created a voltage divider that is consuming this much more power. So it's consuming what's 62 minus 2500? 2440. It's consuming 2400 more watts just because the only way you knew for dividing a voltage or stepping down a voltage was through a voltage divider. So what is the alternative? How can we reduce the voltage and not lose so much power? Because power is money, right? And it's energy, and it's global warming, and it's all that. So how do I create a 25 volt supply out of a 100 volt supply? Anybody? Okay. Are you guys still here? Yes, Imran.
I think the answer should be by turning it on and off.
The answer is actually by turning it on and off. So if I could create a supply, so if I put a switch here, so I don't want these resistors, they're just eating up power for nothing. Instead, I'm going to put a switch here, right? And I'm going to turn the switch on and off. So this is the input voltage, this is the output voltage. If I turn the switch on, I get 100 volts, and when I turn it off, I get 0 volts. If I switch on for only a quarter of the period, so it's on for quarter of the period and off for 3/4 of the period. So it's like this. The average of this DC voltage, the average of this pulsing voltage would be the duty cycle of the switch times the input voltage. So a quarter times 100 gives me 25 volts. So instead of those resistors, I'm going to put a switch, turn it on and off, and then put a capacitor here to smoothen out the voltage. So a capacitor may be a Zener diode, and then I can create 25 volts out of 100 volts with not much power loss. So the reason we need to do these ons and offs is because of power efficiency. We need to be able to handle high powers and high currents with high efficiency. An inverter. So if I have a DC input and I switch it on and off like this. If I switch it like this, so I have a negative and a positive, this is not far from a sinusoidal. You guys probably have studied Fourier series. This, if you filter it, if you apply a filter, you get your sinusoidal waveform plus a number of other sine waves. So if I filter this waveform, I can create a sinusoidal. So by switching a DC supply, so if I give this to a switch and turn the switch on and off, I can make a square wave like this that when you filter becomes a sine wave. So this becomes an inverter. So this is how these switches and the switching systems work, and we'll talk about the different circuits. But then the main reason for switching these on and off is to change the power or create the different voltages and different properties that we want at a high efficiency. You already know how to do it with other means, but we want to do it with high efficiency, low cost, and in small packages. And that means that we need to have these semiconductor switches. Okay, thanks for staying behind, guys. I hope I answered your question, Simran.
Yes, thank you.
Okay, see you guys next time.